ます。
でもアメリカは広い。
でもなんか国立が苦しあれですあるとなんかダメそうな。
フォード飛行機も作ってたんですか？
飛行機エンジン。
あ、エンジンだけ。
飛行機そのものは多分戦争中は多分分かりませんけど。
ああ、なるほど。
ボードのやつある。
なんか嫌な嫌な。
This was little, and they had where did you play in there? They had a little schoolhouse.
Good afternoon. For your safety, we ask that you remain seated. Keep arms, legs, heads well inside. And there is no eating, drinking, or smoking while aboard. Thank you. Lived the first 16 years of his life in this farmhouse. They brought the farmhouse from its original site a little over 2 miles from here. Ford and Greenfield Roads, Dearborn. Miller School, second school that Ford attended, and the brick building was the yellow wooden addition, the Wright cycle shop. The Wright brothers made the first successful flying machine there. And the white home, sometimes referred to as the Bishop's house. Aiken, Ohio. From Menlo Park, New Jersey, the world's first industrial research laboratory, Menlo Park compound. Fascinating place to explore. 1876 to 86. Edison worked on many projects in there. 1877 patent for the phonograph, and 1879 for the incandescent lighting system. One of the first homes to receive the lighting system, Sarah Jordan Boarding House. Victorian home with the lunchroom sign across the road. Sarah Jordan, also known as Aunt Sally. Distant relative of Edison, ran the boarding house. In 1880, she had 16 daughters staying there. The Great Frame Building was Edison's laboratory from Florida. Behind it, the Maddox slave homes from a hermitage plantation outside of Savannah, Georgia. The Acme Covered Bridge, 1832, southwestern Pennsylvania. And on the right-hand side across the road is the test track of Ford Motor Company in the 20s and 30s. And the airport, Time Motor Toulouse airplanes. On the far left, beautiful example of Greek revival architecture, a large white Webster home. Tobacco is growing right here alongside the track. And this is our plantation home at Susquehanna. Around the 1860s, Tidewater regions of Maryland. Beside it is our Little Plimpton House. That's the oldest American home in Greenfield Village, 1640, Sudbury, Massachusetts. Also from Massachusetts in the mid-1600s is our Tower Windmill. It has a revolving roof. And the oldest home is the Stone Cotswold Cottage, England, 1600. Our Great Frame, built in 1740 in Connecticut by Samuel Dagger. They interpret life as it would have been in the 1700s in New England. And that style of architecture is called a snowplow house. If you have a chance to come back and visit this area, look for potatoes with feathers in it they have suspended. Scare the little critters away from their vegetables. Greenfield Village, together with the Henry Ford Museum, is an independent, non-profit education institution.
I'm not prepared to tell you what they are, but they're pretty impressive anyway. Who cares about object-oriented? Well, Darren Strawsup does. He invented C++ in 1979, and every year, not every year, every 7 months, the population of C++ users doubled. So he has this chart in his paper at the history of programming languages that shows that he predicts there's now 500,000 users of C++, and something like that. And Borland shipped 1 million compilers in less than 5 years. As of April this year, they announced they had shipped their 1 millionth compiler. They're one compiler manufacturer. Of course, there are other companies like Microsoft, for example. So Borland cares. They're making a lot of money on those C++ compilers, and many other people are building them. And then population continues to double and sort of taking over the world in some sense. Yet, I've heard people say, that C++ blew it and the industry knows it. I mean, C grew up with C++, and C++ really isn't object-oriented. Well, the guy has a pole in the water, but forget about that. And then but in particular, if you're talking about computing, and if you know what I mean by a pointer, there aren't any things that point into the middle of this thing, It's not allowed. Maybe that's a random pointer sticking out of the water there, but it's not connected to this gondola. And everything has to go through the interface, which is the gentleman with the hat, okay? And so the idea here is that it's an abstract data type. It can be looked at and viewed as itself with its contents and what these contents mean, and et cetera, and it's not connected to anything else necessarily. Well, it turns out that's not quite true, but you have to talk about some other things. But basically, it's an island unto itself. Now, a more illustrative of this is the August 4th, 1986 cover, which shows ice cream in a different way. This is a professor, obviously teaching object-oriented languages in 1986. We'll blow this thing up. Now you notice here, this is an object class that I want you to look at this graph and look at this picture and understand what this means. Everything is an object class, and every little picture there or icon represents a class of objects, pictorially. So you see there's different kinds of ice cream. There's milkshakes, things that are stirred. There are things that come in dishes. There are things that come in little cups. There are things that come in cones. There are things that come with bars, ice cream bar type things. And there are things that come on sticks and things that come in rolls. So this is a way of taking the world of ice cream and sort of saying, hey, this is the way to divide the thing up. Now, there's a superclass and subclass. So for example, there's these ice cream cones, only just like a skeleton or something where the stuff is not filled in, okay? Okay, so these things are called abstract classes. And they're peculiar because they're not real classes. You can't build them. Because what would you do with them? You can't actually ask for the area of something. You can't draw it without having one of the specific things below. Okay, now, what object-oriented does not mean necessarily. Smalltalk, Dylan, and Objective-C are one-type system, essentially. And like Lisp, you don't have to say what the type is. Whereas C++, IFO, Haskell, and System Axiom, which I'll mention a little bit later, is also an object-oriented language, is strongly typed, and it has multitude of data types.
The use of Maple for multi-body system modeling and simulation. First of all, I have to apologize for my bad English. I'm French. I'm working in the University of France and in the French National Institute of Research in Computer Science, culinary. And my special interest is to use Maple or a general algebra system to study image multi-body systems. So I'm going to speak about a software developed in Maple programming language, which is called Sigma, for symbol link generation and manipulation of mechanical algebraic equations. So it is nearly 2 years we are working on this project, and my presentation will follow this plan. First of all, I will present the general architecture of the Sigma. Then I will speak about the mechanical systems we can study. I will say a few words, but really fast, about Higgs formulation of mechanical equations. That is a formulation we have chosen. And after that, I will try to develop a complete session of a software use. So an example, that is how we describe the mechanism, how we generate the equations, how we can visualize and handle these equations. That's important. That's the point why we choose to use Maple, an algebra system, so that we can get the equations, the mechanical equations, and handle them. And then I will speak about the numerical code generation, because at the last point we can generate some complete and ready to compile Fortran or C code generator simulation. I want to say a few words about validation and the future of this project. So the general architecture is in two parts, divided in two parts. The first one is symbolic, that is Maple, and the second one is numeric. It's purely numeric, and we'll see if this can be Fortran or C code. So the first thing to do is to describe your mechanism. This is really simple. I will show you on the example. So you have to describe the mechanism. That is, you say I have one body, I have two bodies, I have three bodies. These bodies are linked together with rotative joints, prismatic joints, things like that. And that's all. After that, you can generate the equations. So we'll see it precisely on an example. Once you've got the equations, you can visualize these equations or handle them. We've got a set of tools dedicated to the manipulations of this equation. And after that, if you want, you're not compelled to, of course, you can generate a full complete simulation code. After that, this is the new normal, I would say the normal shape of a numerical simulation. That is, you enter numerical data, and you've got an integration loop which will integrate the system with time. So what kind of mechanisms can we study with Sigma? We can study a mechanism composed of an unlimited number of rigid bodies. There are two big words there. Unlimited, of course, as soon as you have a computer, you are limited. But normally, we are not limited. Okay, so you can have 10, 12, 15 bodies connected together. The second point is rigid bodies. We don't deal with flexible structure. That will be certainly a point to develop in the future, but for the moment we deal only with rigid bodies. Second thing, you must have a simple kinematic chain topology. That is, if you have a robot arm, your robot arm can't actuate on itself. That makes a closed loop, and that's a big problem for mechanicians. That deals with a lot of problems if you have closed loop. After that, you can the joints between the bodies can be a revolute joint, prismatic joints, or free into space. The first aim for this project is to study the European space shuttle called Hermes with a robot arm on it. So we had a shuttle that is a body with 6 degrees of freedom in the space, and on it we have a 6 degrees of freedom robot arm. That is a 12 degrees of freedom system. That is quite complicated. It was the beginning of the project. And these bodies can be subject to external forces, torques, and of course gravity, if you don't put in space. We have chosen to use King's formulation of mechanical equations. I won't give any technical details on this method, but we can say it derives from Gibbs-Apple formulation, and it's quite easy to use with a computer algebra system, because the equations are purely recurrent equations. So the system is derived as this. We've got a mass matrix for an n degree of freedom system, where n is the number of degrees of freedom. We have a mass matrix Okay, you have the accelerations, that is the second time derivatives of the coordinates, and the force vector, which represent the inertial forces inside the system and the external forces acting upon the system. That is the general form of the equations we get. So we'll go on with an example. So I'm compelled to take a very small example, that is 2 degrees of freedom example, otherwise the equations become really too large to see on slides. So I've chosen to take a 2-body system, body A and body B, and we will specialize the system, seeing the equations, seeing how we can specialize the system, so that we get the classical double pendulum system. Okay. So the important vectors here are the vector linking the center of mass of the body to the hinge point with the body before, and the vector from the center of mass to the hinge point with the next body. These are the 2 vectors we will see always. And of course, for any body, you've got a mass, a scalar mass, you've got an inertial matrix, 3x3 inertial matrix, and you've got other things like that. And we always handle them. We are going to see the equations. We always handle them as names. So here's a session. I'm sorry, I don't have. This has not been made with the Maple 5 release 2. So first thing is to declare your system. You declare 2 bodies, body A and body B. That's a bit. So the only thing you have to do is to declare body A and body B. And you say they are linked with rotational joints. Okay? After that, you only need to give that as data, and you can compute the equations. That is, you compute the equations. And here is one coefficient of a mass matrix. Okay? So I have to explain a bit. It's not really easy to read. So we handle everything as vectors or matrices. You can see there, this is an inertial matrices of body B. This is a vector, a 3x1 vector. This is a vector 2. This is a vector of a hinge. Sorry, I'm too close to see. This is a vector of a hinge, and so on. So we manipulate vectors as names. Okay? And so that we have written our operators. But here you can see a scalar multiplication between a scalar variable, this is the mass of body B, with a big vectorial matricial expression. This is a transposition between matrix. This one is a tilt, I don't know how you call it in English. This means that you have taken a cross product between 2 vectors. You transform cross products with matrices products, and so on. So you see, we have got a large set of operators dedicated to our expressions. So that these operators are useful because we make a lot of simplifications, of default simplifications, as soon as we compute the equations. For example, we put every scalar multiplication at the beginning. So we have a pseudo-canonical form of our equations, and this can be very useful to make simplifications. Last thing you see there's a frame operator. This frame operator, in fact, hides some frame changes. Everybody has a frame associated to it. Okay? And if you want to derive the equations, you have to change frame and to express everything in the reference frame. So you've got a lot of cosine matrix that appear there. Okay? And we think this is not really important, really interesting to see all the cosine matrix here in this expression. So they are written under frame vectors, frame operators like this. But the information is there. This means, for example, that the vector GIEA is expressed in the reference frame of a body A, and we have to express it in the reference frame of a body 0. 0 is the referential body. Okay? And this means that we have to multiply it by a cosine matrix. Okay? And this is hidden for a moment. After that, we can visualize the expressions, you can see them, and we can handle them. How is it possible? We can describe a substitution, and we can describe a few points about the architecture of a system. That is, for example, I want to say that rotational axis of body A, that means L1, is parallel to the first pendulum axis. So I will describe a cross product or a dot product if I want to say something else. And I will say this cross product, this dot product is equal to 0. Okay? After that, I go on specializing my system towards the double pendulum. I will say that inertia matrices are new. Okay, are equals to 0. You've got balls, and so the matricial inertias are equals to 0. And the last thing, you can say that the center of mass of body A is situated at each point with body B. That means that the vector GOB is equal to 0. Once you've done that, you can apply the substitution into your equations. Okay. And this is the same coefficient of a mass matrix as we have already seen. Okay. So that we have replaced everything with 0. We have done this substitution. That means we have introduced some frame vectors within this function, and everything. That's the easiest way to do, of course. You have you call a subroutine, which has already been written, and you don't have any problem. The only thing, this is completely inefficient. Why? Because you make a call, this costs a lot, and within this multiplication subroutine, you will certainly do a double loop. That's not really efficient, of course. So what we have chosen to do is not to generate such calls, but directly to do computation, to do the multiplication within Maple, and once and for all. That is, we will only generate this. Well, this is to fill the two matrices and vector, of course, and we will generate directly the coefficients of the F5 vector, which is the multiplication of this matrix by this vector. So that you will only have to do this and not any call, not any loop within your subroutine calls and things like that. And this is you can save a lot of computational time using this kind of method. So here how we translate our equations, and of course to get complete simulation code, you have to generate some complementary routines. That is to enter numerical data. If you haven't entered the mass of a body, of the inertia of a body within the Maple session, of course you can enter it, you have to enter it if you want to make a simulation. So you have to generate
when you want to introduce elementary quantum mechanics in class, suddenly you met several. You encounter several problems, and the most important and most difficult problem the student should give up to follow classic Newtonian concepts, and that means that it all behaves like a wave, and this is due to the very basic principle Roy's quantum postulate for a particle behave like a waves, and this is very different concept from classical mechanics. So first, how do you introduce this change of very drastic concepts? Okay, this particle duality, wave duality. Okay. It's rather easy to teach students of this type of a concept. It's easy to realize for students to realize that the phenomena in microscopic scales can handle by Schrödinger equations, and it is rather easy. write down that expression to present propagation rate, and you get very many kinds of answers from students. Some students say sine omega t. Some say that the cosine qx and so on, and lots of answers. But say you need propagating wave, not a standing wave. Okay, so finally, say for example, you get we have two variables, qx, omega t. Okay, this is a propagating wave. Propagating waves, then okay, say you differentiate this equation 2 times. Difference this equation by time variables, and just say you finally found epsilon omega equal energy. This is the momentum. Soon this make from this equation you can easily get this type of differential Schrödinger differential equation. It's not just if you were a wave function, particles behave like a wave, then student realize Schrödinger wave function is really basic equation to treat this type of model. Okay, so this kind of interactive discussion with the students using Maple is very effective to understand the basic principle of quantum mechanics. Okay, now the student understand particles behave like a wave, so that quantum problems you can use the Schrödinger wave equation, and this involves some kind of interaction particle wave with potential or the other particles. Okay, what's the interaction? This is a wave. Okay, wave interact with other wave. It's a refraction, transmission, diffraction, interference. There's all the wave-like nature. Okay, so first, if you make a student understand that the particle behave like waves, it's rather easy to extend the basic principle to more complicated problems. Okay, first, I just try to, I don't have enough time, so that briefly show you the example of one-dimensional potential for real problems. Now, the particle is a wave. It's propagate, refract, and this is the straight type wave potential Fourier, and wave refracted, and this means that there is a standing wave and transmission. Okay, then finally you can do some quantum tunneling interpretations. Say Maple do not teach you physics, okay? So what you we select wave function for every region. Okay, why you use this type of wave function in this region? Why you select this expression in this region? One, the propagation and refract. Propagated and refract. This is there is a standing wave, so that there is a real number then transmitter. Okay, this type of things. And we use the simple macro calculation. And finally, you find you get 4 linear equations with the boundary condition here, and finally.
You are teachers, and I am part of a research project at Diablo Valley College where my wife, Dr. Elaine Cohen, is Dean of Instruction. And the research project is, can you get somebody who dresses like an undertaker to wear more exciting clothing like this tie? Please send your comments about how well she did to her address to Diablo Valley College in Pleasant Hill, California. As far as the rest of the humor, Tom has done enough. The subject of my talk is evolution and revolution. If I can get the lights on here. In scientific and engineering computing. Actually, the subject of my talk is what goes on inside the head of a computational physicist, and why does this person use Maple? And basically what I'm going to do is talk a little bit about the evolution revolution back in the days of log cabins when I first started computation, along with John White and a couple of other ancient pelicans that are floating around here. Let me begin by talking about computational physics. It's really a hybrid science, and it deals with making models against physical reality. It also is, these models are languages. Modeling is dealing with languages. To make the models of a physical phenomenon, first of all, you have a physical model. You've already reduced the complexity of the phenomena you're dealing with so it can become tractable. After you have a physical model, what do you do with it? You have to represent it, using another language called mathematics. And finally, you have to compute something. Somebody put on my desk the other day, after I had given a talk on some fairly abstract theoretical solid-state physics, that basically said, it's numbers, stupid. So we got to keep remembering here that my job is to get numbers out. And sometimes I don't obey the niceties of mathematics. I'm reminded of a time in my undergraduate career. I was taking a math course with mathematicians in calculus. And I stood up there, and I was, I think, a sophomore, and we were taught some calculus in our physics courses in freshman year, and I said, I was at the board, and I said dy dx of y equals ax squared, therefore d of y equals ax squared dx, and then you take the integral of both sides. And the professor said, oh my God, what are they teaching you over there in the physics department? That's not mathematics, that's fantasy. That's a single operator. You can't separate d dx from anything. So, but we did it anyway. Understand how physicists deal with mathematics. There's going to be a theme throughout here. What we want to finally get is some representation of phenomena in terms of numbers. It requires the following disciplines: physics, mathematics, numerical analysis, and computer science. It's important to know what these are. It's important to know that in this massive solution space for these 5 nonlinear PDEs, you have to represent, and by the way, they're 3-dimensional. And they also are a function of time. We do a lot of, however, there's a point where there's a point of no return, and we get rid of the time dependence by assuming a steady state solution. Now, we need models for these. We're making models on models on models. How are we going to do this? This is models of material phenomena. Now, we're talking about algebra and calculus. And this insight came to me thanks to Wally and a few others the other day while here. And I said, now I know what I do for a living. I do this. I generate these numbers. I also do this, right? But that's not with my physics hat on. That's with my numerical analysis, computer science, and prayer hat on. Okay. And when we get to algebra and calculus, we eventually get to maple. But there's a long way yet to go before I show you how that happens. I promised a little bit of history in the evolution of scientific and engineering computation. In the beginning was the abacus. And according to Tom, I started somewhere in the Han Empire around 1215 in China, where the abacus was a powerful computational tool. Actually, I started before that in the age of the computer SARS, which is a very well-known prehistoric animal, and it was called the IBM 650. I hear some people who remember it. Oh, I'm not alone. I was at Westinghouse Atomic Power. I was fresh out of college. I had hair, and I weighed 160 pounds. And I thought I was something special. We started, and as I walked into the plant after getting my security clearance, and my boss-to-be, Ray Schiff, said, "You know what a computer is?" And I said, "What's that?" He said, "Good, you're just the person we need." Because they wanted somebody to start afresh. And I came into the room where the IBM 650 was. And those of you who have read the Dragon Rider series of Anne McCaffrey's, who enjoy science fiction, that dragon's egg cracked open and I was impressed. And from that day on in July, actually it's now 38 years ago, this week as a matter of fact, when I started, I fell in love with that blinking light beast. Little did I know how much aggravation it was going to give me up to this time. We had the word software was never used. I never heard the word algorithm. I didn't know that when I did long division, according to the way Mrs. Taft taught me in the 4th grade, that was an algorithm. There was no operating system. There was this thing that blinked, that had biquinary base, that had punch cards going in and punch cards going out, that sat in this monstrous room with a false floor and 15,000 tons of air conditioning because it was all tubes. It had a 1,000-word magnetic drum. There were 3 of us who, quote, programmed it. We didn't know what we were doing. I didn't even know what the word numerical analysis meant. There were some books out. There were some early books before the Second World War. And no, I did not do this before the Second World War. I'm not that old yet. And then a miracle happened. Somebody at Bell Labs named Volantis. And my friend John White and a couple of other of the Ancient Pelican Society here I asked them about that. That they didn't remember. It was an assembly language, sort of. But then IBM came out with a symbolic optimal assembly program. You actually wrote a series of instructions in some symbolic way. You could name the places, the addresses. You didn't have to worry about whether the next instruction was close enough so that it got right under the reed head of the magnetic drum. Heaven. And then, of course, this was a floating point, a fixed point machine. So we got a software floating point interpreter. Now remember what we're solving here. We're solving a second-order differential equation. It was also nonlinear. It is the equation that describes the transports of particles everywhere, including inside a nuclear reactor. We had to know where the neutrons were. It was 3-dimensional, and we were taking a crack at it with this machine. This was a big advance, the IBM 650. The first nuclear reactor designed for the submarine, the Nautilus, was designed on a 20-point analog simulator in cylindrical coordinates. They mushed everything together theoretically. They ran 20 points down the center, the axis of the cylinder, and 20 points along the radius, and put it in the boat and prayed. And that's literally what happened. When it first entered the boat, the electric boat company in the Thames River in Connecticut, it was so heavy that they thought that the boat was just going to sink aft first into the mud in the Thames, with Admiral Rickover standing there looking mean. In a couple of years after I was at Westinghouse, at Westinghouse, we got more sophisticated symbolic assembly programs, and then the real miracle happened. Fortran. In 1956 or so, my boss said to me, "Do you want to go?" I think it was to Endicott, I'm not sure, and take a course in something that takes a new language,
I said, well, is it a new assembly language? He says, no, it's got something to do with you saying you can write down y equals ax plus b, you put in x, you put in a, and you put in b, and you get y out. All right, I'll go. I didn't really want to travel up to Endicott and spend 3 or 4 weeks there, and I walk in the door to the course, and it says, gentlemen and ladies, welcome to the formula translation course. That's what Fortran stands for those of you old enough to remember. And that was a revolution. That was a real revolution. We had a language where we became more distant from the details of the machine. We could solve problems in our own fields without having to worry about some terrible things going on in there, such as allocation of resources. But it wasn't quite that way. If you all remember, you had this pack of cards in front of your Fortran program, and that pack of cards dealt with whatever they defined as an operating system there. Real revolution. In 1960, I went to IIT Research Institute and doing computation of nuclear and solid-state physics, not realizing that I still thought I was a theoretical solid-state physicist. That's what I was trained as. But I was using the computer a lot. They had an IBM 7090, which was a very advanced machine, and I can't remember if that was the first solid-state machine that IBM brought out. I think the 4 digits was the first semiconductor machine. Still needed a lot of cooling. And we had Fortran 2, and then the Europeans decided to try the first precursor to ordering the way you did programming. Those of you who know Fortran know that it's not very structured. And this was a concept of structuring the programs called ALGOL. It was also an attempt by the Europeans to compete with the IBM owned and controlled Fortran. Okay, no revolution really there. It sort of died. But continuing in the beginning, I then went to Honeywell Corporate Research Center in 1964. I interviewed there for 2 days. It was a very tough interview. I never thought of asking to be shown the computer facilities. I just assumed everybody had one. I walk in there on my first day and ask my boss, Don Long, please show me the computer room. He proudly takes me down the hall, brings me in a room with a table, and sitting on it is a Friedan, I believe, or a Martian, I couldn't remember which, an electromechanical calculator. Back to the future. I was very sad. Then Honeywell started getting involved in computers accidentally. They're a control company. They thought they needed computers for control. The next thing they knew, they were competing with IBM, not successfully. But they were getting involved in computers. And after being frustrated, I convinced them, because right down the street was control data. And I had sheer raw power. Sheer raw power. That 6600 was a piece of work. With things that would take me hours on a 7090 would take me 30 seconds on a 6600. Now this is not a complete history, let me be clear about this. In 1982, I went to Santa Barbara Research Center and began to deal with those 5 coupled nonlinear second-order PDEs. And then I got the Cray. Santa Barbara Research Center said, sure, you can go use our Cray down at Hughes Aircraft Company. Santa Barbara Research Center was a subsidiary of Hughes Aircraft Company. I got on that Cray. I never saw anything like that machine. Those of you who've used it know how powerful it is. This was the Cray one, and oh, frabjous joy, I was a happy person. But something was missing. Something was still missing. You get involved in long calculations, you're going to make errors. No human being cannot make errors. Now you can imagine the second-order nonlinear differential equation. I can't remember how many flops that first Cray was. I was trying to think the other day. Maybe some of you know what the Cray one is in terms of fractions of a gigaflop. But it did it so fast and spit out intermediate, the intermediate results were lost in the blink of the eye. And the analytic part of the solution became tedious and time-consuming. And in the late 70s and early 80s, I began to search for something symbolic. And of course, I came across Maxima on a Lisp processor. And how was I going to convince Santa Barbara Research Center to go out and buy a Lisp machine? It was very primitive in those days. It did certain things. And in 19 1983 or 84, my colleague Ken Kosai and I tried a problem with the University of Arizona Optical Science Department that had Maximo on a list processor. We were solving what was a simple problem to set up, and Maximo didn't do it. I'll talk about that problem at the end of my talk. Meanwhile, I became unhappy in having to deal with mainframes. Ever dealt with mainframes? I mean, in the old days, you go to this little window and you hand your cards in, you had one little Fortran error, and 24 hours later it would come back and say, didn't compile. I mean, it took forever to get anything through. You were dealing with the arrogance of the people who ran the mainframe, and I decided that I didn't want to use a mainframe, and everybody said, well, that's easy today, we've got terminals, you just go use a fax. I was getting too old to have to deal with the terminal language, whether it be a Sun workstation and a motif and the Sun operating system. I wanted something easy, and in the middle of 1984, 85, my boss walks in at Sandbar Research Center and plops this little box on my thing. He says, this is called a Macintosh. I ignored it for 7 months. A Macintosh? I'm a big, powerful numerical analyst. I use crays and I use CDC stars and I've used everything from the iliac to the stretch to God knows what. And he's giving me this little box, this toy. Well, I started playing around with it. And I did a lot of the non-calculational things. And then, I don't think this is right. I don't think Maple was not released in 1980. I believe people like Keith Betts at the University of Waterloo were beginning to work on a computational or symbolic algebra system. Somewhere around 1988, 89, I walked into the University of California, Santa Barbara bookstore, and there it said it, Maple. Mathematica I'd already seen, but I couldn't afford $800. This promised me smaller amount of core space occupied, and it was faster. So I bought Maple with my own money. And I put it on my Mac. And I said to myself, wow, I'm doing symbolic algebra on my Mac. And the next thing I did was I got a Fortran for my Mac. I now had it all right in front of me. What took me 3 weeks took me 30 seconds between Maple and my Fortran. It took me 3 weeks going down to the window with my box of punch cards. One day I tripped and 1,200 of them went all over the floor. And if you know, I got a little lazy and I didn't key them in and sequence them, and that was a very aggravating day, but that was years before I learned that lesson. So it was Maple that was missing. Now, I'm going to talk about a little physics here. It gets a little scary. Just pretend you're at the movie Jurassic Park. Hold your neighbor's hand. And I promise you it won't hurt, and we'll go through this as quickly as possible. But in order to get insight into my head, what I do, I need to talk about a little physics. And the first physics problem is related to that design, only instead of talking about an integrated circuit to do digital processing, I'm going to talk about converting light to current. It's a photodetector. You see it every day. You see its actions every day. That's what's in a television camera. A television camera, you use silicon. It's in the visible. For those of us, and my field is infrared, you use mercury, cadmium, telluride alloy, and that detects light in the infrared. And you've seen that in action if you watched the Gulf War. You saw the flares in the cockpit of the pilots, and that's what was in there. Let's go back all the way from that big design tool and get to the core physics. Now, light comes in. This is the physical model that I talked about before. Light comes in and creates a carrier, an electron, a current that moves through the solid. And this tells, when it gets to the end, it says, light was here, and this was its intensity. Light can be considered particles. You needed to hear Professor Abi's talk today to hear how light and particles and waves can exist in the same entity. Only this trip down to the end of the material is not an easy one. It's fraught with danger. It's like a kayaker going down the Columbia River when it's at full bore, right? And he's in this little shell, and this is what the electron in the kayaker does. It bounces back and forth and back and forth. There's a voltage across here, so it's drifting down there. But it's 2 steps backward, 3 steps forward, 1 step back, 5 steps back, and it bounces around in there until it finally gets to the end. But it doesn't always get to the end. It's very dangerous for an electron in its carrier state. It sometimes can die. And that's very important, because if that carrier dies, then we don't know the information it was carrying. If Paul Revere's horse broke his leg, right? We'd have never been able to warn the Patriots in Lexington or wherever. So, for those of you from England, I apologize for the analogy. It may bring painful memories. So the kayaker, the electron, the carrier is bouncing down the material, but a very important phenomenon, its lifetime. Because if its lifetime is too short, this thing won't work, because it won't give us the message. So lifetime is a very important physical parameter. And I mentioned that those device physics equations, those coupled 5 nonlinear PDEs, I can hardly say them, it takes me half an hour, that's one of the critical parameters. It's a materials parameter. This is the part that's scary, coming up. So I want to tell you that right up front. Clutch your neighbor. Just remember, it's a fantasy. It doesn't happen in real life. We need, that model I gave is not adequate. That's not a physical model. That's a concept of how things work. We need to describe it a little better. And we use some fundamental things in physics. By the way, physics is very easy. Physics is very easy. Conservation of energy. The whole system, the energy never changes. Just be careful what you include in the whole system. Conservation of momentum. Once you have those, you're home free. You have to know a couple other things. Forces equals repel, opposites attract. You now have had the first course in physics. That's all you need to know. The rest is detail. So let me just impose that on you. Assume you understand that. In this diagram, I am showing energy versus momentum inside a solid in a schematic way. This is a band of states that has no carriers in them. This is a band of states that is filled with electrons. Because they're filled, they can't change their energy and momentum. There's no place to go. There's no empty spaces, therefore it doesn't conduct. There are no electrons here. How do I get them up here? How do I get electrons up here? Because that's empty, and therefore they can change their energy momentum and zip down in the spatial direction to the battery, the positive battery terminal. Well, I bring in some light. You notice that not all states, whoops. I get a little exuberant and overextended here on my beautiful tie. Don't tell my wife that I clipped on her tie here. We get to the point here where we bring light in. Light has a certain energy. Notice that there's a gap in allowed states in the energy momentum space. There's a gap. It's called the band gap. This is a word that's been bandied around about in the last few years. It's becoming common knowledge, although this is what it is. It's nothing esoteric, nothing obscure. It's just the band gap. If the light has the energy of the band gap, the light particle, called the photon, will kick an electron sitting out here to here. We're halfway home. We have a way of getting electrons in a solid to represent the number of photons in the incoming light beam. We've made the conversion. As Bishop Berkeley says, if a tree falls in the forest and nobody's there, can you hear the sound? That's a big philosophical question. It's a real question here. It's now here. Now let's look in the spatial direction. It's got to get all the way here. And there's a lot of grizzlies, 12th order multiple integral. Don't worry about all the notation. These are wave functions for those of you who get off on quantum mechanics. And This is an interesting problem to solve. And someday I hope Maple will solve it. Thank you very much. Where's Benton? Is Benton here? If not, I will send an email to him and say, this is the next thing we'd like to solve. Actually, you can solve this now with Monte Carlo methods. And I look forward as the improvement in statistical packages in Maple, we will attack this with Monte Carlo. But probably we'll have to use a crane. This is a long, involved problem. In any case, we bring on board conservation of energy and momentum, our old friends, and then we do something that physicists love to do. We make a series of approximations and assumptions. We drive mathematicians crazy. We never show mathematicians what we do for fear of being shot. This particular term is varying quite slowly with respect to the independent variable. We'll pull it out of the integral. Whatever works. I'll give you a story about perturbation theory, which many of you know about. I did a calculation for a quantum mechanics course, and I got the first order perturbation theory, and I stopped. Gave me a reasonable result. My professor of physics says that's fine. And it was a very interesting result, so we were speaking to a group of people, including some mathematical physicists, and they said, how stable is it, Joe, my professor? And Joe said, I don't know, do we care? And he says, yeah. So he had me go back and do second order perturbation theory, which it blew all over the place. Did we care? No. We just published the results with first order perturbation theory and never mentioned that when you went to second order. But what the heck? We have all these simplification tools, etc. This is the first page. Didn't matter whether I turned it upside down, crossways. You get the point. And so I get invited back next year. I'm not going to tell you how we reduce that thing to something simple. In fact, we haven't done it yet. And it's a marvelous test for Maple and its tools. Why do I not put this right in a Fortran program? What am I doing here? This is crazy. You take a 2x2 complex matrix, Fortran can do it easily. I'm a physicist too. I don't lose all that information. I have to, my guts, and I've got a lot of them as you can tell, I've got to feel how alpha depends on wavelength, how it depends on the thickness of the wafers. And this problem is circumscribed. Actually, the interface between two of those layers is fuzzy. It's not a sharp interface. So I'll leave you in suspense till next year. I hope you're all here. I'll tell you how we did it. And I want to thank all the people who have been helping me do it. In summary, Maple is very important to me because it doesn't sweat the details and it does not drive me to distraction with long, complicated calculations that I can never use. I'm at the bottom of the feeding chain, down at the tool-making level, and this is where Maple is really applicable. Thank you very much.
Let you in on a little secret, unofficially. We have saved all the best papers for last, so you shall be rewarded for your faith. And I suspect the papers will get even better as the afternoon progresses.
Can you rotate that up a little bit? That'd be us.
When I first started thinking about how I was going to give this presentation, I thought back to presentations that I had listened to and tried to think of which ones I had found particularly interesting and what it was I was going to learn from that with this. And one thing I found all paper presentations had in common is that they would talk about what I think of as the what and the how, the what they did and how they went about doing it. The ones that I found particularly interesting, though, did a few things beyond that, and they tended to talk a little bit about what I think of as the why, the how not, and the what should I walk away with. The why being what motivated the development in the first place. The how not being the things didn't always go right. And the what I should walk away with being the things that could be extracted and distilled down in some way and perhaps accessible to other people for projects that may not necessarily be terribly related, but would still be good learnings to take. And so that's sort of the framework I'm going to follow with this. And in particular, I want to emphasize using Maple in a particular way. One obvious way you can use Maple is you can use Maple to solve a problem. It's a very relatively straightforward situation. The thing that I particularly tend to emphasize with consultants at MIT who are helping users is the other way to use Maple is to explore problems, not necessarily to worry about the solution, but to worry about understanding the problem in the first place. So, as I talk about the work in dealing with large matrices, I'm going to work on sort of this approach, where I'll show how it was an issue of looking at a problem and trying to find out what sort of the root causes of it were. And in particular, trying to gain some insights about what our users do, what our faculty do, perhaps in teaching students, and seeing maybe if that implies the need to, as a support organization, help faculty in a slightly different way. And then to take a look at the project itself, what the development process was, what went right, what went wrong, to look at Maple and see what its strengths were and maybe what some of its limitations were, and perhaps use that to generate suggestions for Waterloo Maple software, saying, well, this is okay. We went a little bit over in this direction to be better. And then finally, to sort of look at the results, based on what was the sort of target in the first place, just how close I got. Okay, so what do I mean by worrying about large matrices? Now, matrices sort of as a particular example, it's the one we usually run into at MIT, just because of the nature of some of the courses taught there. I'm talking about situations where students solve, or at least try to solve, computationally large problems. And I mean either problems that have a large amount of data, or a large amount of variables, or a large amount of execution time involved. Different students have different situations according to various courses, but these scenarios we run into quite frequently now. In the 2 years I've been at MIT and talking to coworkers and the years they've been there before, this is an ongoing theme, where students
an algorithm for dealing with floating point computation of Grosvenor bases. Grosvenor bases being a very fundamental algorithm for computer algebra in general, in terms of solving systems of equations.
Thank you. My name is Yoshida Erani. I am temporarily visiting Cornell University, but don't guess that my English is good because my stay in US is only 1 year. So I'm sorry, my talk is not maybe proper, but I believe it is quite universal in the sense that it can be applied not only in Maple but also in other computer-driven systems. So, as you might know, Grosvenor basis is a very special set of polynomials called standard basis, such that it yields any polynomial into a unique normal form using this set. So, and Grosvenor basis, trivial example. My key idea is keeping track of the errors derived from the S polynomial calculations and polynomial deductions. So I'd like to introduce bracket coefficients in order to keep track of the errors. It is quite similar to interval of interval arithmetic, but it is very it can be generalized into directions. So, namely, bracket coefficients, or simply BC, is for true coefficient. So the bracket of the approximation of A and the error, so global error. Very simple concept. So today I won't go into detail, but this tool can be generalized. The BC is 0 if and only the absolute value of A is less than the error. So namely, our algorithm is for input is a finite set of real polynomials and a natural number mu. So the output is a set of floating point number coefficient polynomials with precision mu, such that the sequence of G mu linear. So they say there is a problem using naive floating point method. So for all mu, GCD of 2D polynomial is always 1. But the correct answer should be the fifth powers of x plus 1/3. So let's apply our algorithm. So
Looks like the x is missing there in the second polynomial. Is that right? X squared plus 2/3 x there. Is the x there? Yeah, that's you're right in the first.
Why?
I mean the 2/3, the top one line.
2/3.
You're right there. I'm one of them.
Oh,
GCD between two polynomial x squared, second one.
yeah.
X squared plus 2/3 x is missing there.
Yes. Yes. Anyway, the problem is it can give always 1 by naive floating point method. But from using our algorithm from precision 1 to 6, actually the floating point Cleveland basis was 1, but from 7 on, the correct support was obtained. So actually, the coefficient-wise conversion to a true Cleveland basis. And what about the multivariate case? This is the 3 variables and 3 polynomials, zero-dimensional ideal for pure lexicographic ordering. This is the result, the floating point expression of the result of the conventional Babbage algorithm. Because actually the rational expression is very huge. So, and yes, our algorithm gives from 6 on, the correct support was obtained. So I'm not sure why this is so high CPU time. So and I must mention that I'm not using G basis in Maple for the sake of fairness of comparison. And G basis is can be applied over the rationalism only. And more complicated coefficients, including transcendental numbers. So, in my implementation of Buchberger's algorithm, so at the reasonable time it can be obtained. But our algorithm gave from precision 6 on, the correct support was obtained. So even for the precision 100, it took only 8 seconds. So finally, my observation is conventional Buchbar algorithm, although it is over only 2 cases. So I do hope that maybe developers implement my algorithm for floating point G basis. So maybe FPG basis faster than G basis, because by my experimentation, FPGP is sometimes faster than RGB. So that's all. Thank you.
Thank you. We have time for one question or so.
We use broker basis in our Symbolic CAD system, and the problem that we have is the equation we get may have been empirically derived, and something like this is truly needed because the input's a lot of stuff. And I've seen other people who had this sort of problem trying to put a point on the time as symbolic. So I think even if you don't achieve an increase in speed, I think there are problems that need to be looked at.
I hope it will be useful.
Okay, thank you very much.
Thank you, Chairman. On the calculation of a three-dimensional unit group of a grouping, and first we will show introduction and definition, and second, what is the problem, third, calculation, we will show a calculation using Maple software. First, introduction and definition. P is a fixed prime integer, and zeta n primitive Pn, the root of unity. For each positive integer n, satisfying like this equation for n over 1, moreover, greater than 1, moreover, we put an like this, and a finite group Z, we denote by AZ, the ring thing representing the function x to gamma, the category of themes to the category of themes to the category of rings, and AZ over x, the unit group theme of AG, that is to say, it represents the function assigned the unit group gamma and for a theme x. And AZX is obtained by an open subtheme of AG, and canonically contains Z as a constant group subtheme. If G is commutative, the canonical map AZX over Z is an isogeny. For each n, for each then put we put ANG equal AG AN equal AG tensor product Z AN. The normal basis theorem implies the following, like a variation of normal basis theorem. Let B be a local ring and C be an unramified Galois extension of B with Galois group Z. Then there exists a Cartesian product
of B morphisms, like this. And the canonical map is universal for unramified Galois coverings of local ring with Galois group G if G equals Z over Pn represents a function x to gamma, and AZX represents the function like this. In this case, the isogeny this is a universal for unramified Pn cyclic Galois coverings of local rings over AN. On the other hand, we can show the existence of deformation of Wn, deformation of width group Wn to a torus Gmn over An, which contains the constant groups in like Z over Pn, and Wn to Wn over Z over Pn, the universality of the isogeny for unramified Pn cyclic Galois coverings of local rings over An. So what is the problem is for each positive integer n, construct Wn such as above, and Cartesian product, this is fiber product, like this. So this is a very complex problems, and for the case of n equal each, and 1999, one of the authors, Professor Sekiguchi and Dr. Suwa, has done case of n equal each. This is a French paper, theory de Kumma, Alpin, Schreier, Academy of Paris. And we will give the answer. This presentation is for n equal 2 and n equal 3 by using network. And the machine is using Sun 670, the 4 CPU. Main memory is 256 megabyte, and the swap is 1 gigabyte. And actually, with polynomials like this, P is prime and W0 X0 X0 is W each equal X0 plus P X1, W2 like this, Wn equal like this. And with ring, originally groups, finally the ring, and like this, uniquely Wn, A, Z, A is a affine space, and the homomorphisms X equal like this. And Wn X equal Y equal like this, and Z equal X plus Y, and Z dash equal XY, and addition and multiply, and Z0 equal like this, and one dimension cases like this, and the two dimensions, X plus Y equal X0 plus Y0, X1 plus Y1 plus P1 over P, X0 P plus Y0 P minus X0 plus Y0 P, XY equal X0 Y0, X1 Y0, K X0 P Y1 plus P X1 Y1, like this.
calculation is sorry in Japanese because English version is left in Japan. So two-dimensional group structure is like this. XY is like this. X, Y, and so from theorem we prove using a maple and this part to the integer and especially this part d2 is the integer and calculation is like this. It's two-dimensional case is very simple one and d1 and y1 is usually like this and very simple one and but three-dimensional case is very complex because xyz is like this and x, this part is x and y and z and from original theorems and d2 integer and x, y and all part is in what is this part is one integer and this integer shows that this whole structure is with groups and calculation is like a G is improvement. He asks to improvement for algebraic geometry part and probably I think probably Maple is most powerful softwares and manipulating softwares. I think improvement will probably really sleep. Thank you very much. Very short.
This is meant to be a completely interactive discussion. If you have any concerns or questions about the product, the service, or any other aspect of the company or the research group, certainly feel free to express them at this session. Just a reminder after this session, and that will be around 5 o'clock, for those of you who wish to join us, we will be gathering back in the East Room just to say goodbyes and then just relax for a little while. There'll be light refreshments. Our panelists for this open forum are three gentlemen that most of you have managed to probably meet in person over the last 3 days. Immediately to my right is Mr. Ron Newman, Chief Executive Officer of Waterloo Maple Software. In the middle is Professor Keith Geddes, Director of the Symbolic Computation Group and a co-inventor of the Maple software. And on the far end is Mr. Benton Leong, who is the Product Manager of Waterloo Maple Software and formerly of the Symbolic Computation Group. Before we begin answering questions, I believe Ron has a short announcement for you.
I wanted to start by thanking everyone for attending and wandering around, listening to a number of the conversations and being party to a number of the conversations. I'm really excited about the kinds of things that have gone on here this week. They certainly far exceeded my expectations for what was going on. And there's an empty chair up front here. You've stayed to the very end, and as an extra package, as extra part of your package, something you weren't counting on, we have an announcement we were looking to make sometime next week, but because of the nature of the dedicated individuals who stuck it out to the end, and because of how excited we are about this announcement, I wanted to move that forward to this moment. So, who's got the drum roll? A number of years ago, we started listening to users tell us about wonderful things that were happening in the area of user interface. We recognized that we needed to do things in this area. We also recognized that there were some pioneers, and for those, when we didn't have to invent things ourselves, we could pick up the very best products in the world in the area of interface and the area of computer algebra system interface. We thought, what the heck, let's talk with an individual who maybe can help us out. I'm pleased to announce that effective, I guess, yesterday afternoon, Waterloo Maple Software and Prescience Corporation have joined forces. They've merged to go forward in the symbolic computation area. And I'd like to welcome Alan into the corporation. As you can imagine, this is a major step forward, and I think a very important day for symbolic computation, for computer algebra, and a step forward for anyone who uses mathematic tools. Alan's tools, expressionist and theorist, have always been on the leading edge of being the easiest to use. Maple has always had the most powerful symbolic computation engine, and then the merger of the two technologies and corporations was just a natural for us. After years of listening to users beat us over the head and say, go and make this happen, we listened very carefully, and I think it's really exciting to be part of that. So I thought it was only appropriate that we have Alan come up here and join us now that he's the newest member of the team, and he'll be of course a core member of the team going forward. Wonderful. Thank you. So why don't we open up the floor to questions at this point then, and you can ask about some new things now. Yes.
First I have to remark that the Maple engine is a powerful engine, but it's also a silent engine. It's a silent power. And some of my users, and I'm talking about the Technical University of Eindhoven in the Netherlands, have problems with this silent power, especially when they are starting very large problems, like using DSolve or using some linear programming syntax algorithm. And these programs runs about a few hours, sometimes up to the day on a workstation without telling anything. And then there's this beautiful message of the Maple engine is not running anymore. And you lost everything, and you don't have a clue what he did up to now. Was he really busy solving the problem, or was he just busy with expressions? Well, this is the comment there, and I have here a suggestion. Maybe you will take over. There are when I write a Fortran or C program, I put myself some control parameters, which I print them from time to time to let me know what is the advance, how the program is doing. Is it doing well? Is it going in the right direction? Or should I stop it? And it would be very nice if in this inert routines of Maple, which as a user, the only way to change things is to take the code, to change the code, to give it a new name, and again to run it. If there you will have some possibilities of putting control parameters which will tell you if you are going in the right direction or you should stop the calculations. Let's say an output option on every routine, on every procedure. Of course, you have the print level and the trace, but they give you too much information. That's exactly what you don't want. You just want information about the process. This was my comment.
Okay, how's that? Yes, you're mentioning checkpoints. We do have one facility that you didn't mention. You mentioned print level, and that's a pretty crude facility. We do have the info level facility, which isn't providing a user controllable kind of checkpoint, but it is providing information about what's going on, whether it be integration or differential equation solving or whatever. You will get messages out as it goes along to give you an idea of the progress of the computation by setting info level for a particular routine. But I think you are asking for a little more that could be given some thought in terms of whether you would be able to actually stop and change directions.
I can give an example. The next library routines mostly have this option, yeah, such an input-output option, which you can turn, which is used, you can turn on and off, and we give you information about the process. And this is really a major problem because if you want to encourage people to use these packages, you should make it accessible. And if some user after 24 hours comes to me and says, the machine crashes and I don't have any idea what I'm going to do with it, maybe I should try using another.
I'd say that's useful input.
Max might have that feature that you could interrupt, check the value of variables, and then return to the calculation. So, that's sort of
Okay.
We're getting all this on tape too, so don't forget.
Don't record my accent.
We've got to filter for that.
You want to take the question?
Sure. Any more questions?
I'd like to suggest that you form focus groups in different areas. For example, physics. I talk to my colleagues and they say, well, this paper will have this, something that we might do in physics. And say, no, but you can write it. Well, they don't want to write it. They want to have a package. They want to have a physics package, like we've got the calculus package and the and so on. What do you put in such a package? Well, I could think, well, you might want a few things here, but if you had focus groups in physics, then we could perhaps go through physics and say, what routines, what commands would be particularly helpful for students or for researchers in doing physics. It's not your job to think of those things, so you're not physicists, but you contact the community of users. Well, this is just like perhaps suggest things, maybe begin to supply code, maybe if someone identify those procedures, topics that would be useful, and I could see mechanical engineering, electrical engineering, lots of other engineering areas develop similar packages, but you need the input.
Discussion, I would say. So I think that you have to recognize that there's probably 150 opportunities sitting in front of us, and picking the right one. 151, there we go. No, that was on the list already. But with the kind of opportunities we have and the number of diverse users we have, addressing the right concerns at the right time is our biggest challenge, because the size of the maple community is growing so rapidly and the demands are increasing, but we're up for the challenge.
I am a Macintosh user, and of course, I've not been able to see release 2, but Ben has persuaded me that it's going to be worth waiting for. But I guess Wade Ellis kind of scared me the other night when he told me that y'all had incorporated some of Dan Schwab's work into release 2. Well, I was very pleased that Dan Schwab made it possible to integrate up to 50 differential equations in the version which he published early in the spring. How much of this do you change when you incorporate his ODE package into release 2? Will I have to use the same routines, or will I have to make new interface, or can I still go back and use his own ODE package?
Okay, I'll start, and then if I have anything to add to this, Keith or Benton, but the routines have been added into Maker 5 Release 2. The routines that appeared in the ODE package that was in the share library and is also talked about in the flight manual. Those routines are available in Maker 5 Release 2 and they are intact. They work exactly the same way. The only difference is that the names of the routines have been changed. That was mentioned by somebody already, but
Will you still be able to integrate up to 50 equations? His first ODE package did only 4 equations. And then in the early screen, he came out with a new one that he announced over the bulletin board that would do up to 50. He said
share library. So I believe that it does the 4. But certainly, if Dan has the code that does the 50, you should be able to work with that in file release 2. I've got Robert waving his hand at me.
Yeah, I think I hear the following question really being asked. Will Dan's package, as he wrote it, run in release 2, pulled out of the share library?
Right. But suppose I choose to use his package instead of the one that's in release 2, and I still call it up and use his package.
The short answer is yes, and we provide instructions on how to do that in the new flight manuals.
That was Bob Evans from Brooks Colt, distributor of.
Yeah, I'm sure you can. It does still run in release 2, but I also wanted to mention that talking about solving ODEs and how many you can solve, we've also been evolving Maple's facilities through DSolve. And when you're now talking about numerical solutions, we've been evolving that a lot. And in release 2 compared to the previous release, and in whatever release comes next, you'll see quite an evolution in the basic DSolve facilities for numerical solution as well.
I think the issue being raised about going from 4 to 50 is a straight run to cut, not an adaptive quadrature, but a straight run to cut RK4 running on hardware and not on the software floating point emulator.
But that's what
that's the issue.
But for us, we'll make sure that through DSolve numeric, you're able to do that. And additional packages will also be available that other people supply. But through DSolve numeric, you'll get what you want.
Further questions? Comments?
What about the control of the shading on 3D graphics?
Control the shape. What do you
be able to put an illumination model or right now you can shade things based on height or X times Y or various things and go through and say, okay, instead, I've got a light over here or I want to shade it based on some other function. I don't get to put in my own shading function.
Actually, you'll be able to control any number of lights that you can add to the scene, and through parameters that are actually in the procedure call, you can add an arbitrary number of lights. So yes, you can in release 2. So all those things that you've asked for, and many of our other users have been asking for, are available in release 2. We also provided as a part of the upgrade in release 2 contour plots and plotting use of color in order to render information in 4 dimensions. So, for example, you can have an independent color variable that's a function of X, Y, and Z.
Yeah, I'd like to make a suggestion there. I'm sure you guys are all familiar with the NCSA tools and the ability to do graphic things. Alan, you in particular talked about easy ways to do colorization on those things. It seemed to me a whole lot easier to use that kind of a technique with a color bar where you can just drag the thing along and change the spectrum than it is to put arguments into a function call. That's one of the real drawbacks that Mathematica has right now in their clumsy way of doing graphics.
We're looking at it.
I have a question regarding placing EPS files in other applications. I'm sure you're well aware that Maple, being a much improved plotting package, has a lot of utility in drawing applications for placing, say, a word processing document. Is there an improvement possible for doing that prior to the next release?
I don't know about prior to the next release, but I know it has been addressed going forward. I was speaking with the gentleman doing it just the other day. I don't know that there's anything we could do as a retrofit again, because we have to address the number of platforms issue. Do you know anything on that, Ben? I think at this point it was there's a little bit of, it puts things in the wrong corner. Basically, you have to do a little bit of twiddling with the EPS files.
Could that code not be posted to anonymous FTP or something like that?
We could perhaps look at putting that in the share library, and that might be, although I do believe that's compiled in, it's not a library code, so it'd have to be a full executable. I believe that's what it is. You
office is back there. Okay, hold on. Just go zippy do. There we go. Okay. Over there. Hi, Jane. Come on back. We'll do all the introductions after a while.
Yesterday was Canada Day the 1st. They gave us a choice of taking yesterday or
Hello, Myrna.
Hi.